Hi, everyone. I'm not sure if everyone here is from ECE3141 or from other ECSE classes, but it's very good to have you guys here. We've got Adam and Yoong from Telstra. They're both network engineers, and they're going to give us a guest lecture on mobile networks. And I know there's definitely going to be a few people from online at Echo 360, so hopefully there's a lot of people listening. And yeah, thank you all for coming, and I hope you enjoy.
My name is Yoong. It's Adam.
Yeah, just a quick introduction. I started my career back in the 90s after attending RMIT, and after that I worked for Ericsson for almost 10 years, and then moved over to Telstra. So I've been working at Telstra for just over 20 years. For my career, I've mostly worked in radio network design and optimization with mobile networks. Worked across, luckily, fortunately, I've been able to work across many technologies from 2G right through to 5G now. Yeah, that's me.
My name is Yoong. I started around the same time as Adam, almost 20 years now in Telstra. I started as a grad in Telstra. That's a bit, we'll talk about a bit more. I did my engineering degree in Tasmania, and a very small town in Hobart, and I did my master in University of Melbourne. I'm the portfolio lead for the performance optimization of the wireless network engineering at the moment. Adam is in charge of the network leadership. We'll move to the next slide. We're going to cover a few things today. We'll start with some basic facts and figures, and I hope people here know what mobile network is. We'll cover some of the basic 101 and some basic some facts and figures about Telstra, particular spectrum, how to design and how we design and building a mobile networks, the satellite technology, the emerging technology that we use, the Internet of Things, and we'll talk a bit about what the future holds for mobile industry. All right, Telstra network. Not sure everyone's subscribed to Telstra, but it is it's the best and the largest mobile network in Australia to date. We has the most sites. What you call site is basically the mobile towers. We've got one actually just right near the campus where they're building a suburban railroads at the moment. We have about 12,000 of those across Australia. Quick timeout. Sorry about that. And about 2,000 more than any other operator. There's only two other big operator in Australia, that's Optus and TPG network. So Telstra is the third operator, which is the largest one. We invested more than any other telcos to date for Telstra, and we continue to invest more in the mobile network, believing that this is the future of technology for wireless. Just in terms of figure, over the last 7 years, up to about end of financial year 2025, we invested about 12.4 billion into building this network nationally. And about 4.7, which is roughly about 40%, is actually in regional. So Telstra is actively investing in metro and regional. So our focus is not just metro, we also invest in regional. And you would have heard Telstra network in the regional is quite extensive and prolific, and that's the reason why that's our focus, and our marketing strength is basically the metro network and the regional network. So we covered both. Just some big figures. Maybe it doesn't make a lot of sense, but in terms of the data consumption, so people using mobile data, we consume about 8.9 petabytes of data up to like June 2024. That's the figure that we got back then. Petabyte is about 10 to the power 15, I think 15 zero. So it's, in other words, it's they call it the quadrillion, I think, quadrillion or quadrillion. 60 million voice calls and about 100 million SMSs. So it's a lot in daily for us in the network that we're seeing that coming through. So it's substantial. Now, Telstra is also a bit of a, it's inherent in Telstra also we want to be an industry leader. And what we're showing here is what we call the world first. We play a key role in innovation, ongoing innovation, and also pushing the boundary of what's possible in the mobile technology. This slide actually needs to be updated now because we just announced 2 new world firsts. So it should be 72 world first. So in terms of world first, you probably won't see the fonts there, but we won't go into it, but we can share with you what that is. Typically around the new features and the new way of pushing the technology and doing new things that improve the performance and experience of the customers. And that's some of the stuff that we've done over the years. So we got coming up to 72. Besides world first, some of them we didn't make it to world first, but it's Australia first. So there's about 32 of them. So if you put together, it's about 100 of those innovation that we have been pushing and putting into the network and helping the customer to do better and helping the industry to also doing better as well. And a lot of this technology eventually flow into the mobile phone and that were used by the customers and they're seeing those features working quite nicely. We're not the biggest in terms of size. There's actually a much bigger network. Australia is about 44. I looked up in the internet, it's about 44 in terms of size. But in terms of the number of innovation that we push in the industry, we are actually quite, for a small player, we are actually pretty, I guess, well known in the world stage. So Telstra is doing quite well in that front, given that the size of the network we've got versus some of the bigger operators. I just show some of the stats there. So these 3 are probably the biggest at the moment in the industry. I'll pass to Adam now to do the 101 stuff.
All right, thanks, Yoong. Yeah, I guess preparing for this, it's such a, I realised there's so much and how can we fit it into an hour? But I thought I'd start off with something, maybe, how does this work? Good if I knew how to use a computer. Start off with something basic. So hopefully you've all had your coffee this morning and ready to go. And I'm just kidding. We'll start off with something much simpler than that. But that diagram was, it's from 3GPP specification. It shows the whole network, all the nodes. In fact, we're going to cover just a small part of that. And Yoong and I work in the wireless network, so that's where we're going to focus a lot of time today. There's also a core network, hugely extensive core network. Very boring, so just remember mobiles, exciting, core, boring. All right, so here's a simple diagram just showing some key parts of the mobile network. I'm just going to start off with this bit because people sometimes don't think about devices. They're not really part of the network, but they are where the end connection is made for a mobile connection. And these are something that it's where you can best measure the customer experience, and it's where people feel the network. And if we go back in time a little bit here, I brought in some relics from the past. You can see devices have changed a lot over time, but then some things about them haven't changed. So this was my first phone that I had, and I actually used this phone when I was working on the Sydney Olympics. And you can see size-wise, this is my phone now, it's not really much difference, thinner. this one. But you look at the way they're built, I'll pass that around, super robust back in the day. And I don't know if you've ever seen those, they're called buttons. Yeah, so it was really hard, really hard to text while driving back in those days. Yeah, so I've got another one here. So that's an Ericsson one. This is a Nokia, and you can pass them around. They're probably worth a bit of money now. Actually, fun story. That was my first phone, and I used to call my wife on that. And actually, that's her phone over there. I used to call her on when we first met. So yeah, mobile phones, and then it's 2G days. And what was really cool back then was the battery lasted so long, you'd forget where you left your charger. You wouldn't have to charge it up for 7 days. Fantastic. What else has changed? So flip phones became really cool. I used to be good at that. Can't do it anymore. So that was one of my 3G phones when I started at Telstra. I won't pass it around. And then had this sort of flick action. It's all about fashion and being cool on the... and then now today, it's all a bit boring. They all look the same. In fact, that's on that picture there, that's a Samsung Galaxy latest model and a latest model iPhone. They look almost exactly the same. It's not so much about the style and the buttons anymore. It's all about the user interface and the software. So what else has changed there? I mean, what were these phones mostly used for back in the day? Voice calls. Who makes voice calls now? Anyone? What was the last time you made a voice call? So we used to dimension the network for voice calls. We'd go, all right, a customer makes a voice call on average once an hour for 120 seconds, work out how many Erlang that was, dimension the network, how many customers there, etc. Nowadays, it's all data, and data has just gone through the roof, petabytes a day, as Yoong pointed out. So a lot's changed, but some things haven't changed, some of the fundamentals, and that is identity information. So in your phone, you put a SIM card, that SIM card's got an IMSI on it, and that IMSI is communicated to the network. Used to be not encrypted at all, so it was just sent over the air as an IMSI, and then you could do things like you could tie people, you could find people basically. You could set up a fake base station. When people came along, they would do a location area update on there. Here's my IMSI, and you know, right, that person is in this area. It's what some people used to do. That's been strengthened a lot now. We use temporary identifiers that are changed all the time. IMSI's never sent over the air anymore, except in rare circumstance. What else is the same? The phone's still got to perform an important job, and that is handover as you move around the network. So your call doesn't drop out when you drive down the road. Your call doesn't drop out when you drive sometimes from Melbourne all the way to Sydney. But all the way along there, all that path, you're changing not just the radio network bit, but you're also actually switching some core network elements along the way there too. So that's what it's got to do. And it's got to report back to the network all this information so the network can control it. So it tells the network, this is my signal strength that I'm seeing right now. This is the cell I'm on. This is, you know, all this sort of stuff. And then decisions can be made. So important thing to keep in mind. And when the devices don't work properly, we have problems, and we see it in our statistics. Sometimes it's just one device that might be faulty, driving things wrong, and we can detect that. Okay, the next bit. How does the device connect to the base station? Uses the air. The air, we call it spectrum. This is something that you will learn about, no doubt. So we have DC all the way up to X-ray or something. And where mobile networks work in this spectrum, somewhere in this range, right about here, where all the green is. Okay, it's good it's green. So 700 megahertz is the low band, right up to I think 26 gigahertz is a millimetre wave. We're using all that in our network. Next slide. ACMA has this chart. It shows all the different bands, and they own that spectrum, and telcos license it off them. And you can see there's quite a lot going on there. For us, this is how many of our sites are made up. And we don't have all carriers everywhere, but usually we have 700 megahertz and 850 megahertz cells, which we're now using for 4G and 5G. We used to use it for 2G and 3G, and the spectrum's transitioned and reused. So this provides our coverage, low band coverage, and then as we go up, more and more capacity. So these bands up here get bigger and bigger. In fact, at 3.6 gigahertz, we're working with, well, at the moment, 60 megahertz carrier, but we've had 100 megahertz carriers there before. Down at 700 megahertz, we have a 20 megahertz wide carrier there. Okay, so I had a question on the next slide, but I might just ask it now. If this band here provides the most coverage, why do we need to bother with the rest? Yeah, it's all about capacity. So all that data that everyone's consuming now, we can't carry it on those low band carriers. They don't have enough capacity. So we add one way to expand the network, add more capacity, and we do that through the high band carriers. The 26 gigahertz one is a bit special, a millimetre wave, very, very small cells with very big bandwidths. And if you've got a Google Pixel phone, you will find some of that some places. I think at the MCG, actually. If you've got a Google Pixel at the MCG that supports millimetre wave, you'll be having the best experience of anyone. And again, that's where it comes back to devices and device support. So these devices, I think some of these ones weren't supporting many bands at all. And that's another thing we look for in devices. They support more and more bands. Not just that, you can combine these together. So you're not just using one band, you can use multiple, and that's called carrier aggregation. Struggling with this controls. So just on that map, that's the bands I was pointing out, and there's some higher stuff there, and that's where we're operating the mobile network at the moment. This one I kind of touched on, but just to reinforce the idea, the lower bands gives us more coverage, higher band, more capacity, but less coverage. And here's the question that I already asked. Very good. Now, let's get into a bit more of the mobile network. So looking at the tower, and RF design is something I started with. Cell planning, it's called. In fact, when I first started at Ericsson, I'd been working there for about 3 months, and they sent me over to Jakarta to plan a mobile network over there. And I think I didn't even have a mobile phone at the time. There was no network in Jakarta, and we were building the first mobile network there. So I worked with a bunch of cell planners from Sweden in Ericsson, and it was all about how to lay out the network so you get coverage where you need it, and of course the capacity that's required as well. So there's a couple of fundamental ideas here on this slide. One is this honeycomb pattern, and you might have seen that before, not sure. I don't like the colours on that, but don't worry about that. This is typically used for laying out sites on a grid. And the reason for it is 3-sector site, antennas have beam width, I think a half power beam width around 65 degrees we use. So at 120 degrees, you're about 10 dB down. That's at this point here in the middle. So we're going, and that provides a really good interlocking of cells that fit well together with that type of shape. And that's why the site's laid out like this. And you can see, there's typically, these are on a straight line through there, through here, through here. And when we need to get more capacity, you can split that. So that's part of the planning activity. At the end of the day, you can't always get the sites where you want them, so you end up with some kind of hybrid of this. And on the far right-hand side there, you can see our actual coverage map, which is coming from propagation predictions. All right, thanks, Yoong. And this picture is just to summarise some of the things that get made when so we don't just put a site up and that's it. There's a lot of thought goes into it. First thing, location, like I said, where does it fit in with the surrounding sites? Important. How high? 30 metres, 50 metres, 100 metres, 10 metres, makes a difference for the coverage. So the coverage objective is important to meet that. Antenna types, what antennas are we going to use there? What technologies are we going to put there? How do we tilt the antennas? What azimuth do we put them on? So all this stuff is important input. So we have some design tools that help us. We use a tool called Atoll. I don't know if you've heard of that. It's you heard of that one? Yep. So that's doing our propagation predictions and helping us with site layouts. Also can do some other things like estimate interference levels, sort of thing. They're okay. All right. Now we're talking. So some components of the mobile network. We'll go through some of these in a bit more detail. So we have the antennas, the radios, the baseband unit, and the core. Remember, core, boring. All right. So here's a picture of base station. This one's actually in Beaumaris, at the back of the golf course there, Royal Melbourne Golf Course. And it's showing a typical 3-sector site that we build in our network. It's 30 metres tall. And it has some components that you will see. Now, I don't know if you ever look up in the air at these things and wonder what all these bits are, but now you're going to be able to do that and you'll know exactly what they are. So here we have remote radio units. So the radio units, we put up the pole, and there's some good reasons. I'll ask you actually why we might do that compared to putting them down the bottom. So think about that. We have passive antennas here. We have this is a new active antenna, relatively new, so we'll talk about that a little bit in a minute. There's also a tower-mounted amplifier. Do you guys do receiver design? Another unit? Okay. All right. So, what was I going to ask you? Why would you put the radios up there? Pretty hard to get to if you have to maintain it, right? Yeah. Yep. Oh, that's yeah, that's good. That's more, but it's more for the antennas because the antennas are doing the transmission. So the radios, I should have explained that better. These remote radio units are just feeding in. They're just feeding into the antennas. Exactly. Yeah. Reduce the loss. That's right. That's one reason. Another reason, if you're reducing the loss, what does that mean? Need less power. Use less power, more power efficient. These are some of the reasons. Plus, you don't need space in a shelter. So if you're leasing space to put the equipment and paying for a pole as well, it's cheaper to put it up there. So a few reasons like that, but it does come with a maintenance risk. I should have explained this box here in the middle is like a distribution box. So we're having a fibre going up to these radio units, and you can see there's two there on this sector, and this box is splitting the fibres to these two separate radios. Also, we need power up there, so we've got that fibre cable is laid up with copper cable, all in one cable, and so it's carrying, I think, a DC 48 volt, I think it is, running up to these units. All right, now the antenna looks pretty simple, but a little bit more going on inside there. So this is the actual antenna that's up there, and it's a multi-band antenna. So you can see here we've got 4 high band ports, and we've got 1 low band port. These antennas can be tilted remotely. So we've got this AISG interface here, which allows us to control internally some stepper motors that change the phase and change the tilt of those antennas electrically. You can also change the tilt mechanically, and there's a difference. So when you tilt an antenna mechanically, things like the back lobe and side lobes are just getting shifted like this. When you tilt an antenna electrically, it can bring it all down. So it's changing the phasing between the antenna elements inside. And you see the diagram on the right hand side, that little stick sticking out? That's actually an indicator of the tilt angle. So if you're up there on the pole, we never look at this, but that's what that's doing. So it's probably, I don't know, 6 or 7 degrees tilted, that particular one. And there's one of those little things for each, and you can see here actually these little Allen key holes, you can manually adjust the tilt as well, but it's all happening remotely for us. In fact, we did a trial last year where we used the network to control an antenna, and we changed the tilt every hour and between 2 different settings, and we got results for the 2 settings. So across the course of 2 days we could determine which setting was the best, just using network statistics and tests like that. We don't do that all the time. I don't know how long it would take to wear one of those antennas out. It was a question. Okay, inside there is all this going on. So you've got your 4, they're all cross-polar antennas. There's basically 5 antennas in there. Okay. So that's passive antenna, and then this is an active antenna. We call it a massive MIMO antenna. Have you heard about MIMO, massive MIMO? Yeah. So that one that's up there is pretty much like this. There's 128 antenna elements in there. They're dual polarized, cross-polar design. The other polarization you can have, and not used much anymore, is the vertical horizontal. So these are cross-polar. It's broken up into subarrays, and these all have their own power amplifiers. So this is called an AIR antenna, antenna integrated radio. That's what it stands for. And by having the radio inside the antenna, you can do some really cool stuff. Beam forming, and you can actually have a beam point individual people, and do some other techniques. So this increases the spectral efficiency, allows us to get more out of the network. So here's a few transmission techniques I thought I'd just mention. The first one, beam forming. So this is directing the beam of the antenna towards an individual mobile. The second one is a generalised beam forming. So it's not like a direct beam that you could draw a picture of. It's more of a obscure looking beam, and it's using all the reflections that are happening between the mobile and the antenna. So you've got stuff bouncing off buildings and whatever, and by sending signals in all these different directions, they are meeting up at the mobile. To do that, the mobile's measuring the radio channel, and it's telling that to the network, and it's also sending sounding reference symbols, I think they're called, and the network's looking at those as well and working out how to make up this beam forming. Magic stuff. and then we can do MIMO. So what this does is it lets you double the capacity. So now we can send 2 beams to the same user and have different transmission on each. So that's increasing the capacity or the throughput that that user can achieve. And then we can have a multi-user MIMO where we can have multiple beams going to multiple users. And all these techniques are to get more, to be able to handle more data. As you know, the data is growing and growing and growing. Wish people still made voice calls. Okay, radio. So we had a look at these remote radio units. They're saving us feeder loss is probably the biggest thing. You can see there's still feeders there coming out of them, but it's right up at the pole, so the losses are much less. We also have radios down the bottom, and that's what's shown on the right-hand side in a rack in the equipment room. Now the next bit of the network is the baseband, and something interesting's happened here since the GSM days. So GSM days, you'd have a BTS, base transceiver station, then you'd have BSC, base station controller, and the base station controller was in a building somewhere and all the sites are out in the field, and that was just making the decision on when to hand users over. And so all the signalling, all the layer 3 signalling for the radio resource control signalling was going back to the BSC, and it's making decisions like, okay, time to hand over to this cell. What's happened now with evolution is all that's happening now in the base station itself. So we don't have any central controller anymore. There's a link between all the base stations. It's called X2 link for 4G, XN I think it's named for 5G, and they can talk to each other and organise this handover stuff. So they can also share information about load, make decisions of handover based on load as well. Yeah, so that's one of the things the baseband's doing. Also, we have some other features like COMP, uplink COMP. What does it stand for? Coordinated multi-point. There we go. Coordinated multi-point operating in the network on the uplink, and what that can do is combine signals from two different receivers. And so then again, the basebands have to talk to each other for that. Okay, core network. Yeah, so the core network does a lot of the routing of the packets. So we have a connection to the, I'm going to get the nodes wrong now because they keep changing, MME in 4G, which is for the control layer. We have the user plane going to PGW, yeah. And so that's split, and the other interesting thing that's happening now, we don't have any circuit switch traffic anymore. So we used to have circuit switching for GSM, and now it's all gone. It's all packet switched. IMS is the node that handles the voice calls. No transcoding, except when you go out of the mobile network, and we need transcoders to go to PSTN, sort of thing. So that's a lot of things happening in the core. And then what's connecting this all together is, of course, the transport network, and this just depicting at a really high level some of our big transport links that go around the country. Of course, there's a lot more to the transport network than just this, and we're using various technologies there, fibre, microwave, we're even using satellite a little bit, which I think probably better explain here. Yeah. So we call, okay, front haul, That's what we call the connection from the baseband to the radio. And we can actually put those basebands, if we want to, together in a hotel. So you don't have to have them on site. You can have a baseband hotel and just run the front haul out to the radios. And then you don't really need a shelter there, but you do need to have some power and other things. And then there's backhaul. And backhaul is from the basebands back to the core. And that's our radio backhaul. And that brings me to, hand over to Yoong.
Thanks, Adam. All right. Adam talks a lot about terrestrial, so everything's just touch on is terrestrial. So we've been doing that for the last, I can't remember, I think 20, 30 years. It's been really good and very mature network we got today is terrestrial network. So towers, in-building, small cells, that's a lot of those. Satellite is an emerging one, but it has been around for a while. Maybe people are not realizing it, but that's the bit that kind of we want to talk about a little bit today. Today, we got actually like 3 types. Some of you may have heard about it. Geostationary, that's been around for a while. You know, people used to do this big satellite phone in very remote Australia. Especially our country is big. Terrestrial network has limited coverage to cover, remote Australia, especially country Australia, America, and Russia. Medium orbit, and the most recently the LEO, the low orbit. And the difference is probably just shown in that diagram down there, just how far they are from Earth, and geo obviously is the furthest away. There's a couple of facts there: altitude, latency, and apparently the furthest you are, the away from surface, and the latency we got. Bandwidth, how much bandwidth support, and Adam talks about capacity, and if more data is required, it'll be hard to push all those data through the geo because it's got very little bandwidth there. I've left a bit of that require quantity to cover Earth, so it's a bit of a question. So have a guess what would take, how many geo to cover our entire Earth surface? Can someone have a guess? 10? Good. Close. It's about 3. So it's about, if you look at it, the size of it, it's actually like a bit of a, one would probably take about half the size of the Earth, and you actually need about 3 at about a 120 degrees angle to get the sort of the full surface covered. Then you get this continuity of the geo coverage across the entire planet. What about the MEO? That should be more. Yes. So there's about a dozen of them to do that. And LEO is an interesting one. It's probably coming to about hundreds to 1,000. So think about number of satellites now flying above us. It's close to about 1,000 of them. Can you think of an example of the use case? Why would we be going down this satellite path instead of terrestrial? What are the important use cases that satellite just always superior than the terrestrial?
Access to remote regions.
Yeah, that's one. Yeah, that's a good one.
Someone's on like a cruise on a ship.
Yeah, absolutely. If you've ever been on a cruise, think about how do you get the internet connection. And the other big one today is that when you're flying, they provide Wi-Fi. Where are they coming from? They're actually coming from this particular network. Unless they build their own, which I don't know, maybe commercial air flight or air company, they have their own, but as far as I know, this is probably the only viable solution. And we've got a lot of oceans on Earth, and where it's just impossible to build base station on top of on water and things like that. So these are the things. But the downside of that is in building. It's you can't be inside a building and you're under some trees and things. This is not going to help you at all. Actually, I've got a and this is available to, it's actually, you can, has anyone been venture into looking at satellites? So this is the website. They'll show you, wait for it to load, but that's roughly how many is actually up there at the moment. And it's amazing, this is a Starlink page. That's their satellite. And we got other companies as well doing this. So there's actually a lot of them up there. And each one of these color, it's actually a satellite. And there's a bit of a legend there that shows you what type they're using. Some of them are the newer ones and the older ones, but that's roughly what they're looking. And they're always moving around. You can see them. Actually, this is kind of live. When it's load up, we'll wait to see that. Yeah, there you go. So it's actually pretty extensive. It's kind of cool. You can actually click on one of them and then see where they're moving. And then you can see it's actually moving around. So it's covered quite a bit of space, yes.
Are those satellites generally privately owned, like by one telco, for example, or do you share them with other people as well?
Great question. So Starlink would be the provider, one of the provider, and they become a bit of a wholesaler. So they will be selling to Telstra. They'll be selling to each company. And it becomes a little bit, they're not like you could call them, because Starlink is Elon's company, so he kind of pioneering this technology a bit, and he launched all this satellite. It's very expensive, obviously, in billions of dollars, and he had to it's an investment he made, and then he has to somehow recuperate that by selling the services to all the other operators. And you can probably imagine this is being used by all countries and all operators, and we don't know how many, but it's potentially get used by many, many, many operators. So they become a bit like a wholesaler. And they manage it, and we just buy the service from them. And we don't launch our satellite, obviously. So Telstra don't own our, so launch his satellite to get this coverage, but Elon does. Okay. All right, back to the slide. On the ground, that's what they look like. So this is one example of where the satellites can be used as backhaul. So M talks about the backhaul. Typically, terrestrial network backhaul is microwave or fiber. But in this particular instance, it's satellite, because it's difficult to get microwave or fiber into a remote area like this, and particularly a lot of the stations and farming stations and remote community. That's the look. And you got the geo backhaul. They look a bit the same, and LEO. And the interesting one is, I think it called out here, is this tool, maybe the next picture. By the way, the bandwidth, that's the important one. Downlink 20 for geo, and uplink about 1 megabits per second. For LEO, we're going to go up to about 75 downlink and 15 meg uplink. And latency is a big differentiation between geo and LEO because of the distance from Earth. And particularly mobiles, it's very sensitive to latency. So you don't want to send a request for a web page, and maybe takes about 2 minutes for the website to come down. That's not a good experience. But it is what's available today. But LEO does make a lot of difference to what we have today for satellite technology. I was going to talk about this particular, some example here in Victoria, where we had deployed one for the geo, for the bushfire. That's Tambourne Inlet. If someone's know that where that is. And there's another one in Queensland. Just noticing those, just calling out these two antennas here. So for LEO, it's got this interesting way of, talks about handover. So these two antenna, that looks a bit like a lollipop. They picked up two satellites because the satellite's moving so quickly in the sky. They picked them up, and when the satellite move across and the Earth is moving as well, so that two lollipop basically coordinated handover, so we get a little bit better seamless coordination from one to the other. So they basically, when the satellite swing across the sky, one picked up the first one, the other one picked up the second one. So when the first one disappears, the second one gets in enough time to initiate a handover. And the packet will be more seamless. You have these two. And it's got a bit of diversity. So in other words, a bit of a diversity sort of setup to enable that seamless connectivity. Now, this is interesting. So that's actually satellite for backhaul. So basically, we have a terrestrial base station using the satellite as the backhaul to the packet exchange to the core. Now, this is really new. It's called satellite to mobile. It's called direct to handset. Have you ever wonder be able to actually talk to the satellite on your phone? And that's actually can happen today. There's some facts there around the satellite we got, about 643. That's the Starlink that we're using today. And if you have a compatible phone and a plan today, and you have a line of sight to the sky, you can actually reach the satellite network. That's directly through your iPhone and your Samsung latest one. How do we looking with time?
Really interesting to mention that they're using a 2600 megahertz carrier, and it looks just like a cell from the ground. That's what's coming from the satellite. So that's how they're able to do it without changing the devices. Nothing special required in the device, just the right software to switch it on. So they're doing some pretty cool tricks to be able to get that to work.
And some of you may have seen the latest Telstra ad that like a bit of a cartoon, and then the farmer with a sheep and saying something, and then the Earth just shifted to a satellite and then shift back. And some of you might be confused what that actually is about. It's actually about this direct-to-handset technology, meaning satellite can now directly talk to your handset. And what essentially this is doing is building a base station, which is typically a base station on the ground, in the sky, and just blasting the signal down to Earth. And that's how it is. It's actually big antennas on top with a lot of them, and then just shooting down to Earth. And it's very amazing how they can do that. Think about the latency, the signal strength, and everything. So be able to allowing the normal phone that you got today to talk to the satellite directly, and without going through a special phone. And in the past, we used to have to buy an Iridium phone, which is a special satellite phone to talk to the satellite. But now your phone can talk to terrestrial network and the satellite network almost concurrently, depending on which one you're on. So this provides a bit of a safety net for us. So that's the technology, complementary to our terrestrial network. So it's not a substitute. Is a complementary. It's typically for remote area, not covered by our network, which is huge, but very low population density today. Today, what we got is only text messaging. Have you ever been to very remote Australia? You'll be able to use that satellite with the right phone and the right plan, text messaging. Over time, we probably evolve into doing voice call and maybe data. But today, technology available is only text, sending text messaging. It's bit of video. I'll see how we're looking with time. I think we can probably do that one. So that's the ad. Hang on, it's not coming up. Yeah, this is the ad I was talking about. So that's a farmer sending a message, and it's getting up to the satellite, and it's waiting for a couple of seconds. Then the message come back. He's done. In case you wonder what that ad is about.
That's from marketing, not from engineering.
Won't go too much into it. That's only been launched about almost a year from now. Probably not the most publicized, but that's some of the stuff. So connect automatically, so you don't have to configure your phone. It's coverage, of course, beyond our traditional network, and only for texting at the moment. All right, next bit is IoT, so Internet of Things. That's what it stands for. Does anyone know what it is? Ever heard of? It's probably in your daily life as well. It's actually a physical device, a bit like your phone, but it's actually embedded inside devices such as sensors, vehicles, machines. Sometimes we call it machine-to-machine type of application. The use cases typically we got seen today is connected fleets, autonomous drivers, particularly in mine and farming, where they use this IoT to control. Basically, there's no driver inside the vehicles, and then the vehicles just go around collecting ores and then send it to the processing. So that's one for tracking as well, for tracking things that they shipped. They put stuff onto a ship, and then they want to track where they've gone. And sometimes you wonder, my delivery is somewhere in the middle of Atlantic Oceans. So that's how you're tracking it. So they know that application. Utility, so things like monitoring, meter monitoring, so you don't have people coming to your house, check your meter, how much you've used your energy, gas, and water. So that's slowly converting to using IoT. And last, and probably the one that I really like, is that smart farming systems. If you ever have a chance to go to maybe some of the bigger farming area, rural community like Wagga in New South Wales, where I went, you see a lot of these optimized agricultural production method they've used in using IoT to help them, the farmers, to do a lot of work. And I got this interesting story when I went to New South Wales Rural, and they were showing me this thing about a machine where they the feed will drop automatically, and the cow, because it smells food, they'll come in and eat the food. And what that happened when they did that is that there's actually a weight underneath the machine. So they weigh the cow when the cow coming in and eat it. So they know on average, real-time data, how much weight their cows are, rather than individually weighing them. So they automatically have this device sitting in a farm, in the middle of the farm, and the feed just drop, and the cow will smell there's some food or coming and eat them as soon as they step on the weight, and then they know how much weight that cow is, and send back to the farmer, and know, okay, my cows are growing, are not growing, they're about time to be harvested, and things like that. So that's a very interesting one I found. By the way, if any questions, just raise a hand if you would like. We'll just keep going through. I probably talked about this already. Quite a bit of application there. Yeah, so not surprising. And you may or may not be aware of them, but they are going, quite a lot of them. And probably more than our handset today that we use, the population for machine to machine. Some of the characteristics, importantly, because they are used particularly in some of this utility, you bury into the ground you put it into people's houses, it has to be low cost. Imagine this is $1,000, so you can't have 1,000 for each one of these things because there's so many that you need to deploy out in there. And so cost is important, very low cost, very reliable, low power consumption because they also run on battery and you charge your phone, that don't get charged a lot. Like if it's a water meter, there's no power and they have to last like 10 years. So the battery life for these devices sometimes can up to 10 to 15 years. For it to be economically viable as a solution, it has to be low cost and also low power consumption. That's a very main criteria for IoT. And because you don't want to go and change them too often. Eventually you have to, but by that time you're probably going to break even in terms of the cost of hiring people to do those work versus you using an IoT. All right, let's conclude the sort of the technical bit. We'll just go through some of what the future will look like for more mobiles. Very quickly, that's the growth we're looking at for mobile data. So it's an exciting industry, lots of opportunity. What does that show you? Someone tell me. What's the first thing come to your mind when you look at that? Is an exabyte, talk about petabyte, exabyte is 10 to the power 18. So it's quintillion, it's called quintillion. That shows you investment. The money that the industry and they're getting, the revenues, it's a lot, and therefore the future investment in the technology and the advancement of it going to be huge. FWA stands for fixed wireless access, so people using it in substitution to your NBN, which is your what I call a fixed access, so it's fixed wireless access. So that's also becoming very popular. Not that we like it, because the mobile bandwidth is expensive versus a fixed, much more expensive than fixed, but that's going on at the moment. Some of the roadmaps coming up, there's a bit of future stuff around 6G, which is the last column there, the orange color thing. We're sitting at around 5G at the moment, so the middle bit. 4G is the legacy. 3G is already exited, 2G is gone, 1G is, we don't talk about that. It's currently a lot of the 5G developments going on. Importantly is that this bottom bit here, so as we progress, we're seeing increasing speed, latency, and scale of the connectivity. So you can connect more users at one time. You can also have better speed and also lower latency. That's a key characteristic as we progress. And that's important because the demands are increasing, so technology need to keep up with that demand. And we limit the spectrum that we got. So we don't have a lot of spectrum to go with. So we need to reuse that spectrum as efficiently as we can with technology. So it's really the software, the modulations, the MIMOs, and everything, antenna technology, everything, losses for where you put the radio, everything that comes in play a little bit to adding to this whole sort of game of making it a winning technology for us. I think that's pretty much the slide before, but just talking a little bit about what's the roadmap for each one of these looking. Mobile networks at 5G at the moment today. 6G is about 3 and 5 years away. The future 10 years is a little bit hard to say what it's going to look like. But satellite, as I've shown here, it's coming up at the bottom. Now, 6G is an interesting one because it's still in the early stage of the development, so we don't really know what it looks like. We can guess. We can say they have some anticipation around it's going to be in the 100 gig terahertz band, so that's very high frequency. Some sub-millisecond latencies, a bit of sort of speculating what that's going to look like, but the standard's still under development. But that's definitely what's people are actively thinking and lobbying the industry, and to try to make the standard the way they would like it to look like for 6G because it's important. Yeah. All right. That's all actually for today for the technical bit. Hope that's give you guys a little bit of idea what the working in Telstra look like for particularly in the mobile space. Just some of the technology that we're looking at and where we're going. We'll touch on a little bit about the grad and undergrad program for you guys. Sorry, I think the slide was hidden. I'll share that again. All right. Yeah.
You had it up.
I had it before.
This one.
Yeah, cool. Can play the videos. Probably won't play the video. I'm running out of time. How are we looking? Are we okay for a couple of minutes? Yeah. Just play the.
Play the video.
Oh, okay, sure. Sorry, we'll start again. Where did that go? Thank you. That was. Seaside, that's great. All right, just a bit of a short video. So we have a graduate program in Telstra's. We don't have a graduate program coordinator here. I can't speak for sort of the whole program. Just a bit of thing that put here is number one is Telstra being the sort of the 2026 finalist for the most popular technology employer. So that's one call out. In 2025, we're also the top 100 graduate employees. And it's about a 14-month program for whoever joined Telstra. And usually the program take you through a bit of induction learnings and through different departments and not necessarily just engineering. So you get the opportunity to be rotated across. And the programs usually commence around February each year. And it's usually a permanent full-time opportunity. And the recruitment process usually takes place around March and June of the preceding year in preparation for the next year program. There is actually a lot of pathways in Telstra, but in terms of technical pathway, these are the ones that been advertised for 2027, software engineering, network engineering, information cyber security, and technology consulting and solution. And that's obviously change every year. So you can get all this information on the website if you're interested, and get in touch as well.
I think it's a pretty good program. Like in network engineering, for example, you might work, with us in mobile network design optimization. You might go and work for some months with satellite. You might go and work. So you get to try a few different areas before you decide this is where I want to go and settle in. So it's good like that. I think it gives some good exposure.
And if you do get accepted and coming to work in mobile network, you definitely see us there. and our colleagues as well, because yeah, we kind of in that mobile space quite a bit and know quite a lot of people. Yeah, so that's pretty much it. That's all we got today. So any questions?
Thank you. And who's got my Nokia phone?
Your wife's phone or your?
Trying to flog it. Oh, thank you. Sorry.
Oh, I don't remember my phone. I guess as we're moving towards like 5G and those faster, higher bandwidth networks, are there, apart from like power and cost, are there other trade-offs associated with that transition?
I think it's that transition is all about trying to optimize and get more out of the technology. Power is a big focal point, actually, trying to cut that down. And one of the latest things we're doing there is we're putting cells to sleep. So you have all those capacity cells on there, you don't need them all the time. If you can sleep them at the right time, you can still deliver the service but save on power. We have a huge power bill at Telstra. We have some big objectives to cut down on that. So that is something that's coming, and Ericsson put a lot of effort into that. They have their own silicon they develop for the radios, and you know there's a lot of focus on that. There is a lot also, I think, you know, to support. It's kind of like the devices are almost driving the need and the apps and things, and like now I think there's mobiles in cars, there's, you know, watches, there's just so many more, and trying to cope with that. So you know, like IoT, very small, it needs to be able to handle very small, very light data in a very efficient way. These things drive the specification, and the specification is what, you know, results in the network. So I don't know if that answered your question.
Yeah, I can add, like, the thing when moving from, so technology cycles are going shorter and shorter. We used to have, like, we lived with 2G for, like, I think maybe 15 to 20 years before we actually discovered this thing called 3G. And 3G lives fairly long as well than 4G. And what we found is that the cycle is getting shorter. And what this means is, as the cycle gets shorter, you move to the new technology, you have to retire the old one. Think about the station that we built. Like we just talked about 12,000. You had to revisit 12,000 sites to put that technology. So it's a lot of money. Just think about going through all the things that you put out there, and especially the IoT I've just spoken about, they all got to be changed out. Because why? Because they're not going to be 6G capable today, but 6G is going to come. What are you going to do with them? and there's this tensions always around the cycle that we're trying to recycle, but then the customer side, on your side, you have to fork out money, change your phone. That change phone is not an issue. You like it. You all want a new flashy new phone, so that's great. But then there's other stuff in the industry that's not. And the other issues with moving to a newer technology is also we're looking at also this constraint with the EME. That's a bit that we didn't kind of spoken about, is that as we put more technology on the base station, the emission actually come out is actually increased. And you might hear people saying about, you know, I don't want a antenna kind of shooting at me because I feel like there's radiations. And of course, it's all within limits, so we don't do any illegal stuff. Everything's legitimate, measured, protected. So, but it does increase the whole that sort of energy that's coming out, and it's all spectrum it's the cousins of microwave and stuff. So it's all hazardous when you get really close to it. So we need to be careful with adding more technology. There's a bit of a trade-off there, here and there, and cost is one. EMA is another health issues, and also logistics. You know, trying to get ahead with the technology. But it's not just the telco doing it. For it to make sense, the customer will have to also come on board. So it becomes a bit of an ecosystem. It's not just telco driving You know, we're rolling out 6G, but nobody's changing to 6G. What's the point? So you need to sort of come together. Handsets need to be able to keep up and things like that. So it's a huge, huge area to think about. Besides just doing one bit, everything has to come together for this to work.
There's always something new to learn. Sometimes I wish I became a doctor because I just have to learn one human body, but I have to learn like 6 Gs. Yeah, but that's good too. Like new things to learn. It's interesting.
I was just wondering, sort of like, I guess, in your day-to-day work and stuff like that, do you guys mostly sort of work within your team, or do you also work with like, do you have to work with like the client? You said power was a big part of it. Do you have to do like power authority stuff and coordinate with them, or like different disciplines like fire engineers and stuff?
Yeah, we mostly work within our team, but we do some work sometimes globally as well. So I've been part of an ECE working group, contributing there. We have a meeting that I attend in Stockholm with a bunch of operators globally. So there's that industry sort of interworking. And you know, we use that to drive the product the way we want it as a group of operators. But internally, I think we do work a bit. They, you know, often come to us with like the products guys. They might want to have a particular product that gives a customer segment something, you know, extra. Like we want to offer low latency for gamers or for industry or something. So we have to come up with a way to do that from a technical, you know. So there's a bit of that too, isn't there? What else?
I would say it's really what you want to imagine yourself doing in Telstra, and the area is vast in terms of if you would like to have interaction with external utility company, because we need to know what the power looks like to build a base station, then you'll be in a group, choose yourself to sort of wedge yourself into that group that looking after what I call this build and delivery program. So that's one mission. As engineers, we have engineers in that space. We have engineers looking after, like Adam said, the standards. And so Adam's very smart, looking after all the standards and stuff. There's people doing, for myself, like more like management, and there's a lot of other areas. So we all play a bit of a role. As I mentioned, because it's so broad, we can't be everywhere. So we kind of have to divide the people up a little bit. Some people look after that. So the way I would express is that you have opportunity to want to find your kind of look for your own sort of space where you want to be, and kind of reimagine your path a little bit in Telstra, because it's so vast, and then we involve with a lot of things. And the good thing about mobiles is because it's a growing technology, and we don't know what 6G entails. Maybe 6G require different things now, and then we have to stand up another group, another mission to look after certain things. Like Spectrum is one, and handsets, we've got handset group. If you're interested in handsets, we've got handset device groups, look after devices. I know very little about it, although I know something about it. We know something about it, but we don't deal with it day to day. But that's an opportunity for you to feel like I actually want to get into the handset a bit more, because I want to deal with Apple, I want to deal with Samsung. That's the opportunity we've got, okay? So there is actually people in Telstra, a daily engagement with Apple and Samsung.
Yeah, there's a lot of work. That's a good example, because there's a lot of that interworking. Like we can make decisions about parameters on the network, which can impact on battery life of devices for the customers. So there's a lot of that sort of thing going on. AI and machine learning and automation is all the rage at the moment, and we have massive amounts of data. So you can just imagine, from all those base stations, from all those connections, there's just so much data coming in, all sorts of things, and we are scratching the surface on what we're doing with that at the moment. So there's big opportunity there. You know, we need good software people who are good with those sort of machine learning techniques and things like that. You know, it's sort of new for us. We know what to do. We don't know how to do it.
Especially in AI. There's a lot of talks around AI how the AI play in the mobile industry, and yeah, it's definitely a lot of room in that space, which not a lot of us actually, we kind of know a little bit, but we're still kind of trying to work out what it look like at this stage. So some uncertainties, there's some exciting stuff, but we're all looking at it, I mean, kind of positively what that's look like.
Just a quick question on the topic. How much of AI-enabled networks are currently in use in 5G? So we have this talk about AI native 5G going to be the next big thing. And 6G, of course, has that capability, is expected to have that capability. But at present, are the networks still somewhat traditional and are not ML-based, or are they AI-enabled networks?
We actually have we have some AI algorithms running in the base stations, in the baseband hardware already today, and it's doing things like link adaptation, changing how the link adaptation works. The link adaptation changing, you know, modulation coding schemes, and making these decisions on the fly, what's best for the customer, you know, device to get the most performance. So there is some AI-enabled features already, and it's more of that coming, but it's probably not the thing you were thinking of, but that's sort of even at that sort of low level in the hardware. Yeah. Yeah, yeah, and then further up, there's a thing called RApps. So this is something, we don't have that quite running yet. We do have some automation in the network. This is where I get confused with all the terminology with the AI and automation and this, how much of this and that. We're doing a project with Melbourne Uni at the moment, which is all about using these sort of techniques to decide on where to put the traffic within all those carriers, how to distribute it in the best way. Because, you know, my phone might be on 700 carrier, Yoong's phone might be on the 1800 carrier, and we distribute people variously. And how we do that can impact on performance. So how do you do that best? Not just statically, but dynamically as customers are moving around, as time of day is changing, morning peaks, afternoon peaks, all this sort of thing. So yeah, that's another application.
And Adam's right. It's just to add on AI. It's emerging, and we can see its potential, but there's still a bit of a, I guess, maybe come down to these trust issues. How can we do it reliably without impacting? And like it or not, mobile technology is slowly becoming like a critical services. It doesn't used to be, but now it's becoming more and more. And people couldn't, I guess you couldn't tolerate, you know, even a couple of minutes without data sessions. And because of the usage and the applications becoming more critical, and if it's like, for example, IoT using the control autonomous vehicles in a mine, you can't stop that for an hour because there'll be lost of, you know, hundreds of thousands of dollars for the business. So it becomes so critical that we sometimes have to think about how do we do this reliably. So AI, we're kind of at a bit of a road there, trying to explore how good it can be, what it can help us, what it can't, what we can trust it to do, and what we can't. But there's still a lot in that space that we're looking at.
Any other questions from the audience? Yes.
I have a quick question. So when you have LEOs that come based on communication, now your handsets wouldn't necessarily be able to transmit to that distance, right? Because low Earth orbit should be what, around 100 kilometers from the Earth's surface. Usually your handset would be able to communicate 40 to 50 at max. How does the uplink work?
Yeah, I mean, it doesn't work inside, but if you're outside, you actually have enough power in the mobile for that to make that link. It's not, you know, it's not a super quick link that you're making. So it's You can use a lot of redundancy in the communication to extend that to the maximum, and it only works outside. And I don't know even if it works that well if it's like super cloudy. So it's really pushing the limit. In the satellite, what they can do is really focus in the gain of the antennas, and so that the more gain they can put in your direction, the less power you need to use to be able to communicate up. So that's the other trick, what's happening in the satellite side.
So is it going to be very small data rates and high overheads?
Yeah.
Okay.
Yeah, absolutely. Yeah.
So
Small
ideally
data rates.
just maybe messages, but nothing more.
That's why we only have messages now. Some light data is possible, but it's going to be, then you've got the capacity of that satellite cell, and it's quite a big, what's the area of them on the ground? I think they're kilometres
50 kilometres
in
by 50.
size, and they're projecting them down. And those satellites are moving pretty quick. So I think, is it 20 minutes or something? They're passing by, and in places in Australia, there's gaps, there's holes, depending on how built out the constellation is that is passing in that direction. So there's all these challenges. I think the big challenge will be trying to get voice to work over it because of the delay. So it's more of a delay. Delay is more of a problem than the coverage part.
And the strength is actually in the satellite technology, that how the satellite actually handle those shifts. Remembering a terrestrial network, you're talking to a fixed point. The mobile is moving, but you're always talking to a fixed sort of infrastructure. But this one is not. The Earth's moving, you're moving, the satellite's moving too. So it's like a really complex thing. The amount of the shift in the signal, sending up, then the next one coming in. So there's a lot of that to deal with. So the power is actually within the satellite itself. That's why it's so funky, I think. Like be able to do those kind of stuff at that distance and still maintaining good. And by the way, it's not seamless. So the ad I just shown you is not like immediately you send something, you get it. But there is a latency. You can see there's a bit of a latency. So it's not as great as what you can do on your terrestrial network, where you can just browse something, watch a YouTube. It would be pretty horrible if you watch a YouTube using those kind of technology, because it's quite delayed. There's still massive delay. Right? You're going up and come back again. Okay, still massive delay.
I just wanted to say thank you on behalf of the cohort, as well as me and Guthrie as well, for coming in today. It was really great to have you guys talk to us and obviously connect a lot of our learning to what we're actually potentially thinking about as doing later in life.
Thank you. Thank you for having us.
Yeah, thanks for having us.